In this chapter, we're going to be talking about chemical kinetics. In the previous chapter, we talked about thermodynamics, and you know that for a reaction to occur, it has to be both thermodynamically favorable. You now know that delta G has to be negative for a reaction to be thermodynamically favorable. And the other factor or criteria that must be met for a chemical reaction to occur is that the reaction has to be kinetically favorable. It has to occur fast enough. If it's too slow, then the reaction's not going to occur. And we have looked at some factors already that speed up reaction rates. We've run many experiments this year where we've used hot plates. And in many cases, that was to speed up the rate of the chemical reaction. When you increase the temperature, particles move faster. They're more likely to collide effectively, and we'll take a look at the collision theory in this chapter in great detail in a couple of days. Other factors that affect reaction rate include concentration. We'll explore that in great detail in this chapter probably tomorrow, and surface area. And we'll look at these factors and how and why they affect reaction rate. So for reaction to occur, it has to be both thermodynamically favorable, which you now know how to determine, and kinetically favorable. And we're going to look at kinetics in this chapter. We're going to link kinetics to equilibrium. Equilibrium will be your next chapter, and you'll be tested on both together. Chemical kinetics defined is the study of reaction rates and factors that affect them, as I said, concentration, temperature, surface area. And we'll be looking at these factors in more detail tomorrow with heavy emphasis on concentration and rate laws. When you want to determine the rate of a reaction, it's really not difficult to do, but first you need to understand or remember that a rate, very simply, is a ratio. And many of you have your driver's licenses already, and some of you probably already, unfortunately, have gotten your first speeding ticket. Not yet? This is getting better and better. Nobody? No. But some of you have sped already. Here come the stories.
Apparently you're not supposed to go 60 in school.
In any event, if you are speeding and the cop gets you with his radar, don't keep driving. You'll get arrested for that.
Wait.
You speed up.
You don't speed up.
They'll stop chasing you after a certain point because it gets too dangerous.
Okay, so let me just share one story with you. I remember driving to my old school one morning with my husband, and this kid had to be doing at least 80 in what I'm guessing was a 35-mile-per-hour zone. Clearly driving like a lunatic. The cop comes out, chases him. The kid pulls into a space in the parking lot, and the cop is not happy, and the kid's, he's been removed from the vehicle, and his hands are on top. And I look, and I go, oh, crap, honey, that's one of mine. And I'm like, this is just not going to be a good day. And I'm just trying to think if we were discussing kinetics then or not quite. But in any event, when I saw the kid later in the day, I'm like, what happened? He's like, well, I did get a big ticket, and the cop wanted to take me to jail, but I told him it was FCAT today, so he let me go so I could take my FCAT. I was like, where do you guys come up with this story? In any event, when the cop pulls you over, your heart starts to beat really, really fast because you know you're in trouble and you're going to have to tell your parents. No, you don't lie. Huh? No. So, the first thing they'll do is they'll, license and registration, and then they'll play a game with you, guess that speed. Do you know how fast you were going?
The speed limit.
Underestimated. No, you clearly were probably going over the speed limit if you got pulled over, unless you had a broken taillight or something. But they'll play a game with you. In any event, hopefully you can talk your way out of it, but don't hold your breath anymore. I've heard that's really quite difficult. But where this is all going with kinetics, which we've now recorded, is that it is far more informative to express your speed as a rate than just saying you were speeding. And he is going to write on that ticket how fast you were going.
90 to 40.
Yes. You were with your mommy and she got one?
No, I have a question. So, like, what if you like, pull onto a road and there's like no speed limit anywhere near you? So how are you supposed to know what it is?
Just go for it.
Don't do that. But you have driven around this county, well,
What if you're in like another place? You don't.
If
well,
you're in like Germany.
if you're on a one-lane road, it's probably not 60, so err on the side of caution, right?
Yeah.
Germany's very different. If you've ever been to a foreign country, the speed limits are much faster, and
But they're in kilometers per hour.
it's kilometers per hour, and it's really like nothing I've ever seen before. It's you really have to be careful. And there was somebody from another country in our lab, and she wanted to go somewhere, and I was like, oh, I'll drive. She goes, no, I have to learn my way around. All it took was one time. I'd never get in the car with her again. Whoosh! It was forget it. She was
I mean, was she going crazy speed or did she just
everything. I just couldn't wait to get out of the car. Never again. Anytime we had to go somewhere, she rented a car in San Francisco too when we were there, and I was like, oh, this is not going to be good.
That's like when I drove with Abby. I'm so scared.
Oh my God.
Thanks for embarrassing her.
No, I was a good driver.
We're all
right.
live television.
In any event, rates. You want to, they are ratios. And it is far more informative to express speed as a rate. If you say the car traveled at 75 miles per hour and the speed limit was 55 miles per hour, clearly you're going 20 miles per hour over the speed limit. Now in New York, if you were going over 25 miles per hour over the speed limit, it was an automatic loss of license. That's not the case in Florida, although one of the kids in sixth period told me if you're so much over, it's actually a felony. So guys, make wise choices.
Wait, the cops can't stop you.
Is this a driving question?
No,
If you throw something on a bus window, it can be a felony.
legally, depending on the weather conditions, a police officer can't give you a ticket unless you're going 15 miles per hour over the speed limit.
And I'll tell you right now that isn't true.
It's
And we'll
depending
discuss
on
it.
the weather conditions.
We'll discuss it at the end. In any event, rates are not always constant. They're going to change as the reaction goes. Same way when you drive. You don't just get in the car, put cruise control on, and drive to Tallahassee. You're not going to make it. All right? You will need to stop for gas. So here's constant speed. That's the cruise control that you've set, where you can determine either an instantaneous rate, say at this point in time, where you would have the distance over the time, or you could get an average rate just by getting the slope of the line, very simple, similar to the way we did our very first lab. You could be accelerating. Let's say you went to the rest stop, used the restroom, got a snack, get back in your car, you're going very slowly, and then poof, speeding back up. Or you could be decelerating, and this is when you're driving, you see that police officer, and at the very least you're going to take your foot off that gas pedal so you slow a little bit. You don't usually want to slam on the brake because they're going to see your brake lights. So here's decelerating. And chemical reactions occur very similarly because reactants first have to find one another to react. They need to collide effectively for a reaction to occur, and we'll talk about the collision theory next time and the time after that. But generally speaking, the reaction starts off very slowly, it picks up speed, and then it'll slow again once one of the reactants is very close to being used up. That is the limiting reagent. So the same way when you drive, you have changing speeds. You'll see that reaction rates will change over time. When you're talking about a chemical reaction, the rate that you're talking about is referred to as reaction rate, and it's an experimental quantity. We'll take a look at some data to learn how to determine reaction rate. What you're going to be doing is measuring either the disappearance of reactants or the appearance of products. So for example, let's say, for example, you've got reactant going to product. What happens to reactants as the reaction goes? Do they get made or used up? They get used up. They get consumed. Products get generated. They get produced. So reactants will disappear and products will appear as the reaction goes from left to right. And typically what you're going to do is you can measure the change in mass in reactants. As the reactant goes, the mass of the reactants will go down, the mass of the products will go up over a time period. You can look at changes in concentration. If you have gases, you can look at changes in volume over time. In the lab, we're going to look at color changes. You'll have two clear solutions. You mix them together and they'll turn blue-black, and we'll measure the time it takes for them to turn a different color. You can also look at acidity. For example, if you generate proton, your acidity will decrease. If you generate hydroxide ion, your acidity, let me rephrase that. As you generate proton, you get more acidic. As you generate hydroxide ion, you get more basic. So these are all things we can look at, but primarily we look at concentration. And concentration is represented with a bracket. For example, we're in the process of making solutions for your next lab, and I am making a potassium iodate solution, and its concentration, which is represented with the brackets, is 0.020 molar. So that's my unit there, which in this case is molarity, moles per liter. Okay? Now when I do express it as a rate, I'm going to look at the change in, remember from the last chapter, delta means change in, concentration over the change in time. Lowercase t for time, concentration brackets. And you're going to learn how to write rate equations with the unit here typically being molar per second, or you could have molar per minute. I like to write it this way, although sometimes it is expressed as such. Okay? And that's all in your notes there. So what we're going to learn how to do is write a rate equation, and this looks nasty. It's really, really easy, so you won't have any issues here. We have a generic equation where the uppercase letters are the substances, the lowercase letters are the coefficients, A and B are the reactants, C and D are the products, just as you saw in the previous chapter. You can write rate equations or rate expressions, and be careful with the nomenclature there, because next time we'll get into rate laws and they differ from rate equations, so be careful there. So for the reactants, when you write a rate equation or expression, you'll have rate is equal to, reactants always start with -1 over the coefficient of that reactant, the rate of decrease in the concentration of A. We know that reactants get consumed, so their amounts will decrease over time. The other reactant, again, -1 over the coefficient, rate of decrease in the concentration of B. Now look at the product rate equation. How does a product rate equation differ from a reactant rate equation? +1 for product, and the amount's going to increase instead of decrease. Okay? So nobody wants to write all of that out. That's just too much. So instead we do it this way. Here's reactant, which you would recognize because you have -1 over the coefficients, change in concentration of A over the change in time. This would be for B. If you have products, you've got +1s, same setup otherwise. And you can set all of them equal to one another, reactants and products. You can have reactant to reactant, product to product, reactant to product. You can have anything. And typically you don't have all 4, you just have 2 of them. So it'll be pretty straightforward. And I'll illustrate that for you here, and then we'll do a few examples so that you feel comfortable with it. In this first generic example, you're making 1 sandwich from 2 slices of bread, 3 slices of cheese, and 5 slices of turkey. Reactants get consumed, products get made. And you want to write a rate equation or expression that shows the disappearance of one reactant and the appearance of one product. So your rate equation starts with rate. Pick whichever reactant you want. I just picked the first one. -1 for reactant over the coefficient. Change in concentration of bread over the change in time. Here's the product, +1 over the coefficient, change in concentration over the change in time. And let's walk through a few examples together so you can see how this works. You'll be very successful with this. In the first one, we're reacting magnesium with hydrogen chloride. We're going to generate magnesium chloride and hydrogen gas. And we're going to write a rate equation or expression that shows the disappearance of one reactant and the appearance of one product. So we write rate. I'm going to pick this reactant. Reactant -1 or +1? -1 over the coefficient. Change in concentration of that substance over the change in time. Lowercase t for time, uppercase T is temp. Be careful. Now we're going to pick one product. Which one would you like to pick? Magnesium chloride. +1 over what? 1, the coefficient. Change in magnesium chloride. You need these brackets like this because that indicates concentration, change in time. Easy peasy? The second example is magnesium reacting with aluminum fluoride to form magnesium fluoride and aluminum. And it says write a rate equation or expression that shows the disappearance of an element. Which element disappears? This one. In addition, we've got to balance this, otherwise we're going to make a mess. You guys are all balancing gurus, so we won't worry about that. We have to pick the element that disappears. This is an element versus a compound. Element, 1 capital letter. -1 or +1? -1 for reactant over 3, the coefficient, change in the concentration of magnesium over the change in time. And which, it says appearance of one product. No, it says appearance of a compound. Sorry, reading the wrong one. So that'd be this one. So positive or negative 1? For a product over the coefficient, change in concentration. That wasn't a very good bracket, sorry. My pen slipped. So this is a rate equation or expression. And just be careful of the nomenclature. So now that we know how to write rate equations, we want to be able to solve them. So if I give you this piece, can you give me this piece, or vice versa? So I might give you the rate at which magnesium disappears, and I might ask you for the rate at which magnesium fluoride appears. So as I mentioned, most chemical reactions do show changing rates, and you can calculate the rate from either rate equations and or from data, and we'll look at both. So in this first example here, I just want to make sure the wording is clear, because this is really the only place, well, I guess the math could be a minor issue. We've got the decomp of dinitrogen pentoxide to nitrogen dioxide and oxygen gas. It says the rate at which nitrogen dioxide forms is 0.0072 molar per second, and we want to know the rate of change of oxygen gas. What we're given is the rate at which nitrogen dioxide forms, and that's 0.0072 molar per second. We want to know the rate at which oxygen gas forms, so this is what we're looking for. We're going to write a rate equation with these two terms, if you will. Both are products, both have positive 1. The 4 from the coefficient, change in concentration of nitrogen dioxide over the change in time here. Positive 1 over the coefficient of oxygen gas, change in concentration over the change in time. This replaces the whole fraction, because this is molar per second. Be careful, there are a lot of kids get confused. So we're going to plug this in for this whole piece. And then 1/4 of this is equal to this, because 1 over 1 is, of course, 1, is 0.0018 molar per second. Let's take a look at a problem from scratch so we can see what's going on. I'm going to rewrite the equation as I read it for you. Hydrogen reacts with 2 moles of iodine chloride to generate iodine and 2 moles of hydrogen chloride. So that I rewrote. It says the rate at which hydrogen chloride forms is 0.0090 molar per second. And we want to know the rate of change for the other product, iodine. And this is sometimes where the confusion lies. They're not clear on what it's actually replacing, what it means. So the rate at which HCl forms, it doesn't include the positive 1 over the coefficient. So be careful there. and we want to know the rate of change of iodine. So I'm first going to write a rate equation with those substances. Then I'm going to replace this term with that. That's 1. This is what I'm looking for. I'm going to call that X because it's easier. And that's going to be 0.0045 molar per second. That is the rate at which iodine appears. Okay? The next problem, it goes with the same equation, so let's hold on to this equation. Questions here? Pretty straightforward? Just watch the math a little bit. It says if the rate at which iodine forms is, so this is a new problem using the same equation. If the rate at which iodine forms is 0.050 molar per second, we want to know the rate of disappearance of the other substance. So what would be our rate equation here? Who's got it? Chris, what do you got? Go ahead, Katana.
So it would be -1.
Well, hang on. She may be writing it different, so she could be fun. If you said -1, were you talking about the reactant or the product? Okay, so go with the reactant right here.
And then it would be the dot snot and then
What's going right here?
2.
Good.
Concentration of iodine over delta T.
Good.
And then equals positive 1 over 1. And then the same.
That's fine. So you opted to put this one first, and that's perfectly fine. So this is 1 over 1, so we won't worry about that. So we have -1/2. This is what we're looking for. We'll call that X. And this is 0.050 molar per second. Now this is baby algebra that you probably learned. It's like pre-algebra that you probably talked about in 7th grade. Be careful. You want 1x and you've got -1/2x. So you need to multiply both sides by the reciprocal of this, which is -2. Question or bless you? And you'll see that substances disappear have a negative rate of disappearance here because they're getting consumed.
Ultra K, they can't see.
I have who?
I think you can just move it down.
Oh. So that's the rate of disappearance here. Not so bad. Is it so bad? Come on, you love it. I'll let you try one. Try the one at the top of the screen. I'll do it too. If the rate at which magnesium disappears is negative 0.300 molar per sec, calculate the rate at which the element appears. Don't forget to balance the equation. I don't know why these say solid. It's kind of stupid. That should say aqueous. So should that. Otherwise, it's not really going to go.
Oh yeah, Dr. Davis.
Yep.
On the test where you put,
I still have some non-takers. But I'll answer maybe privately. What'd you get? Huh? What'd you get? That's, yeah, just watch your ciggies. That's what I got. You balance it. Here's your rate equation. Solve it. And it's positive, right? I don't know if that's clear to you. Is that what you got? Questions? So you now know how to write rate equations. You know that kinetics is the study of reaction rates and the factors that affect them. Not only can you write the rate equations, you can solve them. And you'll get some more practice with this. Ideally, I would like to go over determination of rates from data. And it's extremely easy. It's not anything that you wouldn't be able to do. But rather than zip through it, I think what we'll do is I'll give you your classwork. And on your classwork, I'm going to write this over here just because it got a little squishy. You can do numbers 1 and 2 only. I just want to make sure you understand the wording. we'll get into writing rate expressions and determining rate of change over interval next time. We'll get into the collision theory next time and start to get into rate laws. We'll do that Thursday and Friday with a lot of practice, and that will get you ready for your quiz on Wednesday. All right, questions? You're good?